Hello and welcome to the next in the research series seminar series. My name is Julie Marsh and I'll be giving today's seminar on sample size calculations. Thank you for those who are attending all the different sites and for those watching on the catch-up opportunities as well. It's only just 12:30, but I'll just push on with some of the housekeeping. Okay, so just before we start, for those who haven't attended one of these seminars before, over the course of the year, these seminars cover a range of topics across the whole research process from conception to completion of a project. Each is designed to be a rapid overview of the topic, and we can't possibly cover everything you need to know, for example, about sample size calculations today in 1 hour. I mean, it's a whole unit of study and something that I'm still learning myself even after 20, maybe getting on 30 years now. Okay, the handouts are provided that direct you to additional resources and other training opportunities where these are appropriate. All seminars are recorded and available on the web the following week if you wish to revisit material or let others know who can't be here today. Importantly for us, please fill in the brief evaluation which is sent to you at the end of the seminar. We're committed to continuous improvement, and your feedback is useful to help us improve and enhance future presentations. As other sites are joining us by video link around WA, please hold questions until the end so people on and off site can hear them with the benefit of a microphone. So there are many ways to do sample size calculations, and there's many options on the internet and 3 services that you can use. I pondered this for a long time and decided to keep with the PS software, just because it's been around for quite a long time. It's familiar, it's tried and tested, and this is just to give you an overview. If you start using other sample size calculators off the internet, then use several of them and make sure they're all coming up roughly in the same ballpark. I realised it wasn't plausible for me to go around and validate every single sample size calculator on the internet and to present on those. And similarly, you never quite know when one is hosted, if it's not going to be updated or if that site's no longer going to be available in the future. And hence the reason this is quite old software. But it's reliable, it's tried and tested. And again, this is just to give you an overview of sample size calculation. My goal today isn't to tell you how to do your sample size calculation for every single study, experiment, and retrospective case control study or clinical trial. It's just to introduce you to all the concepts. So I'm going to cover this in terms of a few of the ethical considerations, a little theory, actually using the software. My particular expertise is in clinical trials, so considerations within that area, and also where you can get some statistical help. What I would say at the outset is if you have access to statistical support, always use it and always double check your sample size. Because performing research is so expensive that if we get the numbers wrong at the very beginning, it's good to have a check. Or maybe there's another colleague who's a little bit more numerate or a bit more comfortable with doing this. And also go online and have a look. Other people doing similar experiments with similar outcomes in similar target populations. What sort of sample size did they have? So much as we'd like to come up with our research hypothesis and our objectives and then determine that the sample size, what is usually more apparent is the sample size is determined by the resources available. We have to focus on the balance between the burden and the risk inherent in the research versus the clinical and scientific value of the research. I hear a lot of backwards and forwards discussions around, is it ethical to do small studies? I mean, particularly relevant nowadays with the COVID-19 studies, everyone's rushing to design and complete, especially when the numbers drop off and you're unable to collect all of them. So studies can be considered unethical when it's not possible to draw objective conclusions. However, I'd put a caveat on that. With small studies, they still can contribute towards meta-analysis. Okay? They provide useful estimates for groups who are difficult to recruit. So if it's a rare disease, for example, the constant answer of inconclusive studies over decades and decades, particularly in clinical trials, is not necessarily an acceptable answer for those individuals living with particularly the chronic conditions. And also small studies are appropriate for if you're doing pilot work, to design maybe the next stage within the same protocol, or if you're designing a whole new piece of research or a whole new protocol. And after all, in theory, if there's no burden or risk to the individuals or to the participants, then in theory any sample size is ethical if you approach it from that point of view. And there's more arguments set out in the paper in the reference at the bottom of the slide. So getting on to the nuts and bolts of sample size calculation. Okay. The sample size controls the precisions of the conclusion by taking into account the variability, the statistical method you use, and the effect size. So today, to simplify everything, I'm just going to look at one statistical method, and that's the comparison of two sample means. But we're going to look at we're going to look at the magnitude and the direction of the effect size, and we're also going to look at the variability of the measurements. So when we're talking about accuracy and precision, you can see that the picture on the left is accurate, yeah, but the different bullet holes are quite spaced out, whereas on the right, it's not as accurate, but it's much more precise. You get that grouping of shots together. The other things we need to take account for in our sample size calculation is how much risk are we willing to put into this study? I mean, rather than taking a sample, what if we took the whole target population? How feasible is that, and what are our resources? So inherently, we have risk when we do our sample size calculation, and those risks are around detecting a difference if it's present. So how much power do we have in our study? If there truly is a difference, will we be able to detect it? The other risk is of declaring a difference if it's not present. And we call this the significance, or the type 1 error, or alpha, it's often denoted by. In the same way, the power can also be spoken of in terms of 1 minus beta, if you see those parameters just sort of thrown around. Yeah? So we don't want to make false conclusions of an effect which isn't there, or not detect an effect which is there. They're both risks that we have to manage when we perform a sample size calculation. Okay, and for those who get a little bit scared about algebra, I've tried to rip out as much algebra as possible from these slides, but I'm afraid, being a mathematician, it just wouldn't be the same if I couldn't throw in a little bit of Greek, so apologies. You can always close your eyes, put on very dark sunglasses, and hopefully it won't induce too much violent reactions in the audience. So closely related to hypothesis testing is confidence intervals. And often if you calculate a confidence interval for the difference between two treatments, it really isn't that different to performing a hypothesis test. So first of all, I'm just going to remind you what we know, or what we hope we know, about confidence intervals to begin with. So we're just going to consider a very simple situation, a normally distributed outcome. So you'll be familiar with the classic bell-shaped distribution. Okay. And we're going to look at the sample mean. So in math speak, we would say that x bar, or the sample mean, approximates to a normal distribution with a mean that takes the value mu, and the standard error is given by the standard deviation divided by root of the sample size. So that's, if I can get the mouse to work, that's what we're looking at over here. I'm just going to deviate briefly to talk about the standard error. So when we perform sample size calculations in a frequentist framework, what we're doing is we're looking at what if we took samples again and again and again. So rather than perform just one trial, what if we did the same trial over and over again? We have this concept that the sample mean itself has a distribution, and we call that the sampling distribution. So if I took everybody in this room at the moment, who are all wonderfully COVID-19 spaced, and measured the average height, I would get a value for the average height in this room. If we went around the other locations dialed in today, I could calculate the average height in each of those rooms as well. And then we could plot what's called a sampling distribution for mean height. And that's what we're looking at when we talk about the variation. So the variation in the sample mean. So the sample mean is our estimate of the true population mean, mu, and it has a variation, what we call it standard error, and that's the standard deviation within the sample divided by the square root of the number in that sample. So you can see where we're coming at with the sample size calculation. The bigger the number of individuals we study, the smaller our standard error is going to be. So what we're interested in when we look at these, when we keep drawing these bell-shaped distributions like this, the reason statisticians get obsessed with the standardized normal distribution is because we know the area under this curve gives us a probability. So we can refer to that as 95% or 0.95. Yeah? So the probability of having a value between minus 1.96 times the standard deviation and plus 1.96 times the standard deviation, or in our case, we're looking at a sampling distribution, so it's the standard error. The probability of falling within this range of values is 95%, or 0.95. Now you can calculate this out for all different values of what the mean is, and what all different values of the standard deviation is. So you're going to get different shapes. So if your mean is 100, it might be based here. If your mean is 150, this whole curve will shift up in this direction. If your mean is only 50, it will shift down here. So you have translation along this axis, depending on what the mean value is. But the standard deviation is the shape parameter for the normal distribution. We're interested in when it's a standardized normal, the standard deviation is equal to 1. As your standard deviation increases, as this gets larger, you're going to flatten off the shape of this. So it's going to not peak as much, but it's going to have much longer tails. So the standard deviation determines the shape of this curve. If your standard deviation is smaller than 1, you're going to get a much more peaky distribution with a really high peak and much shorter tails. But the reason we're interested in this is we want to know the probability, and we can only calculate that from the area under the curve. Now imagine, so when I first started out doing statistics, we barely used computers, everything was done by hand, including all those regression equations and calculating out what those coefficients were. So we used to walk around with our statistical tables, and every single day I'd be looking up the values to answer questions in those tables. What we couldn't have was a bunch of tables that told me the area under the curve for every different normal distribution you can have. So what if it had a mean of 5 and a standard deviation of 4? What if it had a mean of 10 and a standard deviation of 0.5? That would have been a huge volume, masses and masses of tables where I would have to pick up the right volume for the right value of the mean and the right value of the standard deviation to look up these values, the area under the curve, so I can get the probability. So instead of that, we did a neat trick, and you can make every normal distribution can be standardized to the standard normal, which is centered around the value 0, and with a standard deviation of 1. And you do that simply by taking the sample mean, subtracting the true value, and dividing by the standard error in this case. And this just converts every normal distribution to be centered around the value 0 with a standard deviation or standard error of 1 in this case. And it just means we don't have masses and masses of tables of stats. Of course, nowadays, it wouldn't make the blindest bit of difference because it's all just looked up on a computer. So the important thing just from this slide is that for a normal distribution, between minus 1.96 and plus 1.96 times the standard deviation, or if it's a sampling distribution, the standard error, values of the mean between here, under this area under the curve, there is a 95% probability they will lie in that region. Or in math speak, we just put that into the equation there. So the only reason we standardize it, the only reason we subtract the mean under the null hypothesis and divide by the variation is so that we can read off values for these area under the curves and get probabilities. So if we replace Z with the formula in this equation, sorry, the algebra's nearly over, don't worry. So instead of Z, we replace it with that x bar minus mu over here, and we know the area under the curve for that is 0.95. Okay, we can rearrange it, and there you'll just see the classic equation for how we calculate a 95% confidence interval. So it's x, mousey? It's x bar either plus 1.96 times the standard error, or it's x bar minus 1.96 times the standard error. And that's your classic formula, x bar plus or minus 1.6 times the standard error for your 95% confidence interval. So our interpretation of that, of a confidence interval, so intuitively, it provides a range of plausible values for a parameter. And that's probably the easiest definition you're ever going to get for a confidence interval. These are plausible values of it. If the value's any greater, it's going to be right out on those tails of the normal distribution, which is highly unlikely to occur. We're saying that the bulk of the probability is right in that shaded yellow section. It's far more likely it's plausible. If you put it in the frequentis framework, because we're dealing in taking samples, we're not looking at everyone, we have a target population, we take a sample from them, it's a concept that if we take repeat samples again and again and again, so if a very large number of random samples are collected from a population, and a 95% confidence interval is computed for each of those independent samples, then the true value of the parameter will lie in about 95% of these intervals. So I would always switch the intuitive ones and just think this is a plausible value for the true population parameter, for the true population mean in this example. So what about if we were just guessing the sample size? So if we had two sets of data we collected here, and all the red data comes from the red group and all the blue data from the blue group, and I plotted them as histograms, roughly histograms that looked a little bit like that, would you say there's a difference between them? So what we're looking at here is there any overlap between these two groups? And you can see that there is no overlap. It is highly unlikely that the red group and the blue group are the same. So with this variation, with this difference between the two means, it's probably extremely unlikely that these two groups are the same. But what if we make it a little bit harder? What if we make the difference between these two sample means close together? So you can see the original plot's over here, and now we're looking at the sample mean. We've reduced the difference down to only 0.1 of a kilogram. Now there's a huge amount of overlap between them. Could you now say that the red and the blue group individuals are different from each other? Or is it by random chance that in this particular sample, the blue group happened to be a little bit heavier than the red group? So we have to find more of a mathematical way to find that sweet spot, that we're not studying too many individuals. Because remember, we only have a fixed amount of resources. We're trying to find that sweet spot at which we can say exactly how many subjects are needed with confidence to say whether the two groups are different or not, whether we can detect a difference or not. So getting back to the clinically relevant difference, because that's the other thing to take into account. Yeah? So a preeminent statistician in the UK called Stephen Sten, rather amusingly, I think, said the clinically relevant difference is that which is used to justify the sample size but will be claimed to be used to find it. This is not how we should do research. We should define the clinically relevant difference up front and then do the sample size. So the next question is, what happens if we increase the variability? So again, the original plot is up here, and this time, instead of a standard deviation of 2, we increase the standard deviation, and now we get the overlap again. And once you find the overlap, you can't definitively say whether the blue group and the red group are different from each other. Okay, so as you increase the variability, you need to increase the sample size. Because remember, for the standard error, so this is the sampling distribution of the sample mean. Yeah, the standard error is divided by root n. So the greater the sample size, you're going to be able to control the size of the standard error. So the other thing that gets bandied around in sample size calculation is significance. And this is the only time when people start talking to the statistician, and all of a sudden we become important and an answer's needed in the next 10 minutes. It doesn't matter, the trial has taken, a year to design up to this point. For some reason, the sample size has to be churned out in the space of 10 minutes. Take your time, consider all the options, collect your evidence to support the parameters that you put into your sample size calculation. But going through exactly what the significance is, so in the previous example, we have, if you now consider this red curve here, the null distribution, and you consider the blue one here, the alternate hypothesis, so the null hypothesis and the alternate hypothesis. So say this is looking at the difference between two groups. What you don't know is if you get a value that overlaps between the two of them, does that truly belong in the red group or the blue group? So we artificially set a value of 5%, and because it's two-tailed, we allow 2.5% to go in one tail and 2.5% to go in the other. And we say that if we get a value in these tails, we think it's highly unlikely that it comes from this distribution. And in this case, probably more likely it comes from the blue one. So for up here, it comes from the blue. And so a two-tailed test, we say it can either be greater than, or you could think of another distribution down here, which is, yeah, so we say that it's not equal to. So it can be less than, it can be greater than, but if it's in the tails, and there's only 2.5% of it being in that tail, 2.5% being in that tail, we're going to say, okay, we're going to consider the null hypothesis is incorrect, and the two groups are not the same. So that's our type 1 error. If it truly does come from this red distribution, and it falls in the tail, and we reject it, that's a type 1 error. But again, it's that risk management. We're willing to accept the risk that 5% of the time we're going to be wrong. And that's considered an acceptable risk level. And significance comes from R.A. Fisher, from the very early crop work he performed at Rothamsted what was it called? I can't remember what it's called, the Rothamsted Station in the UK. But it was all around crops and repeated samples from areas of the field that were divided up in all different ways. So again, acceptable risk, significance level, we accept that 5 times out of 100 or 1 in 20 we will be incorrect. Okay. So the other thing, the last part we got to, so we've looked at what the clinically significant difference is, we've looked at the effect of the variability, we've had a look at the significance level, now we're going to look at what the power is. So the power really comes from 1 minus the type 2 error. So the other error that we can make is what happens if the value truly falls under this blue curve, which is the alternate hypothesis. What if it truly belongs in here, but it falls in the tails of this distribution? So the true value is that it should be here, but it's in the tail. And we've decided that in these tails, we're going to reject the alternate hypothesis, or we're going to fail to accept anyway the alternate. Okay? So again, if it falls in the tail here, we're far more likely to say that it's from this red curve, from our null distribution, when truly it belongs in here. So that's the other type of error that we can make. Yeah, so we fail to reject the null hypothesis when there truly is a difference. So the power refers to this white area all over here. So when you hear things like there's 80% power, there's 90% power, what it's saying is that you detected a difference and you correctly accepted that there was a difference. Okay, and that's at 90%. When you hear about beta or your type 2 error, that's referring to that little blue area down there where we make false conclusions. So in this particular example, how far apart they are with a clinically significant difference of 0.6. Yeah. There is a power over here of 96.7%, which is pretty large for a study. And again, this is another risk that we're willing to make. Usually, we would allow the power to be somewhere closer to 0.8. And the way we've done that is to reduce the size of the clinically significant difference, or the difference that we're able to detect. We've reduced that difference, yeah? And we've reduced the power to detect something appropriately. And again, these are just what is acceptable in the literature. You normally have either 80% power, or in some studies you might have 90% power. And they're just kind of rules of thumbs which we've come to accept Yeah, these are acceptable levels of risk for type 1 errors and for type 2 errors. Using all of this with a simple comparison of two means, there's a nice easy sample size where you can just plug numbers into a formulae. So lots of algebra here, but don't worry. This is just saying this is the variability. This is just saying this is the difference. So the standard error squared, the difference squared. And these are standard normal deviates that apply to the type 1 error, or your alpha and your beta. So I'll show these with an example. So Z alpha upon 2. So it's a two-tailed test. We take alpha and we divide it by 2, because remember there's two tails on that red distribution. And that's the value of the standard normal distribution, which gives an upper tail probability of, for example, 2.5%. And then Z beta, again, is an upper tail probability for that 80%. Remember we had the 80% in the blue distribution in the middle was 80%, so there's 10% in each tails. So you'll notice that as the standard deviation increases, your sample size increases. As your difference increases, n decreases. Yeah? So those two distributions are closer together. Yeah? You need a larger sample size. As the two distributions are further apart, you need a smaller sample size. Oops. If you increase either significance or the probability of a type 2 error, n increases. So increasing either of those. So let's just plug numbers into a formula. You'll see how straightforward it is for this example. So here it's placebo-controlled. It's a parallel group study. The outcome is FEV1. The clinically relevant difference we're looking for is 200 millilitres, so that gives you your delta. Your standard deviation, whoops, where is it? Your standard deviation is 450. Okay. It's two-sided, so when we look at our alpha, that's going to be alpha upon 2, and that's at the 5%. And we want, it should say at least, not at last, at least 80% power. The formula is given in the top right here. So specifying all of those values. And that's for your classic 5% at 80% power. Substituting those values into the formulae, we get 79.38 per treatment arm. However, it's really difficult to only recruit 0.38 of an individual, so we tend to take the whole person. So always round up. If you round down, you might be just on that border, so always go up. And remember, these are completing patients. So when we say you need 80 per treatment arm, you may need to increase that due to loss to follow-up, dropouts, individuals who withdraw from the study, anticipated missing data values where you can't get back any information about someone. So you do your sample size calculation, you just plug the numbers in quite simply. In this example, you always round up the number required per arm, and then remember that this is for completing patients. Patients who provide information, data, and don't withdraw from the study. So you also need to increase it to allow for anticipated dropouts, missing values, and anything else that can be anticipated on the trial. So in practice, there's many different formulae for calculating the sample size, depending on what your type of outcome is. I've only shown this so far for the outcome for a comparison of two means. Okay, there's also binary outcomes, there's ordinal outcomes, there's survival, time to event. The study design may be a parallel group or a crossover. You may be looking at longitudinal analysis or survival analysis, proportional odds. There's your study objective. So I was looking to detect a difference. You may be looking for non-inferiority or equivalence. And the underlying statistical methodology you use itself determines the appropriate formulae to use. The best book I've found in this area is written by Stephen Julius, a colleague in the UK, which is a tutorial in biostats, and there's a reference for that in the handout. Okay, so in the next 15-20 minutes, we're just going to take a whirlwind tour through a package called PS, which originally I think came out in about the 1990s, I think, so it's been around a while. There's a few more versions of it. It seems to prefer Windows to using an Apple, but that may be updated nowadays. I don't know. It's been a long time since I downloaded my version of the package. And obviously it's not really something that I use routinely, but you'll see it has some nice features, which is the reason I've chosen to illustrate things using that today. So these are the designs that are available within there. Just your classic case control studies, your cohort studies, survival analysis. And remember, when we're doing experimental designs or clinical trials, you're normally thinking about cohort studies. So when you download the package and you click on the PS icon, you'll get this pop-up window. And so you just obviously click continue. And you'll see it's quite an old-fashioned template. And across the top here are the tabs that allow you to choose what type of analysis you're looking to perform. So I'm presuming this was designed for statisticians in the very early days. So for example, if we want to look at continuous response and we want to do like a two-sample t-test for the test of two means, we would just click on the t-test tab. Oops, sorry. And then it will produce some information just to remind you of exactly what you're planning to do. So this just automatically pops up in the package. It's not something I'm expecting you to read now. It's just that a lot of blurb. So just in case you don't use it very often, you can just refresh your memory. What is it that I'm doing? Okay. So the important things is once you click on that tab, it will ask you to enter the sample size. So there's drop-down menus. So you select you want the sample size. It will also let you, for a given sample size, look at what the power would be back in the opposite direction. We're just going to look at sample sizes today. So click on that. And then we're looking at independent samples. So from the drop-down menu here, and then entering all the numbers that we've just used in the previous example. I've put in a significance level of 0.05. I've entered a power. Is the mouse showing? I've entered there it is. I've entered a power of 80% or 0.8. I've put in a difference of 200 and a standard deviation of 450. And then you just click on the button, calculate. And when you hit calculate, the only other thing to bring up in this slide is it does allow you to do unequal allocation. So that M over there, where it has the value 1, if you wish, you can have different numbers allocated to placebo and your intervention, or the comparator and your intervention arms. In all of these examples, I've just assumed equal allocation between all of them, so M will always be 1. So you hit calculate, and it will fill up the description window down here. And the great thing about that description window is that if you wish, you can literally just cut and paste it into a protocol or any sort of research document that you're writing up. And it spells it all out, and it tells everybody else what assumptions you use, what values went into the calculation and everything. So as you can see from the written text there, it says we're planning the study, continuous response, one control for every intervention. It tells you it used the standard deviation of 450. It looked at the difference is 200, it's an absolute difference. And it tells you exactly how many subjects are needed in the experimental arm and in the control arm. So that's the other advantage of this particular sample size calculator, is it gives you the blurb that you can cut and paste if you wish. If you're not familiar with what needs to be included in a power calculation, you can just cut and paste it out and put it in your document, because it will specify everything you need. Having said that, if it's a grant application, you've probably got about 2 sentences, so you're going to have to work hard to collapse that all down to fit in. And that's it for calculating a 2-sample t-test. So going through just a couple of other features, options on here. So if we want to do a paired 2-sample test, I've highlighted here the drop-down window. Instead of the word independent, this time we bring up the word paired. And if we put exactly the same values in this time, for a paired test, you'll see that the sample size this time is dropped down to 42. Because the within subject comparison is always a lot lower variability than what you would get between subject comparisons. If you're doing a cohort study, so that includes your tests of 2 proportions, or if you're comparing odds ratios or relative risks. So really, if you're doing anything like a randomized controlled trial. Right. This one I clicked on the dichotomous test. So this is looking at proportions. Here is it. You get the usual blurb that pops up. And so for tests of 2 independent proportions, in the first window over here, we select that they're independent. In the next one, we say it's perspective. So we're moving forward in time to collect our outcomes. We're looking at 2 proportions. And in this particular example, I've selected Fisher's exact test. I think they also have the chi-square test in there. Oops, where's the mouse? There it is. And then we've got the 5% significance level, 80% power. And I've said the proportion in the first group is 40% or 0.4. The proportion in the intervention group is a reduction, and that's gone down to 0.2 or 20%. Equal allocation, and then again you hit the calculate button. And when you hit the calculate button, it will give you the blurb again in the window here. And this one tells you that you need 91 experimental subjects and 91 control subjects. Just moving swiftly through a couple of other examples. So if you're doing a matched case control study instead, so it's still that dichotomous outcome, but this time we're interested in odds ratios. So once you hit on matched or paired, it will only give the option of a case control or another. It will give you, if you select case control from the next drop-down window, and this time we enter your alpha and your power. You put in the proportion in the baseline group. So again, 40%, equal allocation. But now over here, there are 2 other things that we have to provide. And one of those is the correlation coefficient for exposure between the matched cases and controlled. So how similar is the exposure in the cases and the controls? So in this particular example, I've put in a value of 0.1. And then the actual difference, in this case, it's a ratio that you're looking for. Oops, where's the mouse gone? There it is. And then the clinically significant effect that we're looking for this time is an odds ratio. And it's a ratio of exposure in the cases relative to controls. And we've put in what is a multiplicative factor of 0.5. So we expect a 50% reduction from the control. So you can see the control value at the moment is 0.4 or 40%. We're expecting a 50% reduction, so that would bring that down to 20%. So it's just two different ways of relaying pretty much the same information, depending on the type of analysis. And in this case, the design, because these are matched or paired case control study, whereas previously there were two independent groups. And again, you get the blurb in the bottom description box, which you can cut and paste into your study. And this one, it says 128 patients with one matched control per case. And then finally, survival analysis, if you're doing a time to event. So we've traditionally called it survival, but I think more accurately we should call it a time to event. So you click on the tab, you get the usual blurb that gives you all the information. And first off, we're just going to look at what if it was a simple log rank test. So in this case, again, we're looking at sample sizes. In the drop-down window, we're going to select 2 survival times. So, because you can specify this in several different ways. Usually people like to just specify what the 2 median survival times are. So, down in this tab, we've got our significance level of 5%, our power of 80%, and over here, M1 and M2 represent your median survival time in your control and your intervention group. So I've done the difference between 2 years and 4 years, or it could be 2 months and 4 months. It doesn't matter what the unit of time is, as long as all of these boxes are filled in with that exact same unit of time. So if you specify one box in weeks, all the other time boxes have to be in weeks. And that's often where sample size calculations go wrong, is they look for a difference of maybe 2 months difference in survival times, but then they put the follow-up time in years. You have to keep to consistent, it has to be consistent. So I'm looking for the difference between a median survival time of 2 years compared to a median survival time of 4 years. And then the additional information you need is the accrual time, so that's the length of recruitment. So we're going to recruit patients over 3 years, and the follow-up time as well. And in this case, we're going to do an additional 5 years beyond that. And then you just hit calculate. That will give you the blurb. And again, it says planning the study, 1 control for each experimental subject, accrual time of 3 time units, follow-up after that of 5 time units. Prior data indicates 2 time units on the control. Experimental ones is for 4 time units, and then it gives you the number needed per group. There's a big difference going from 2 to 4 years, and so this is a tiny sample size calculation of only 42 per group. You will more likely get values in the hundreds per group. Alternatively, you can put that whole power calculation again, but using a hazards ratio. So the same values as before, but rather than 2 median times down here, we've still got in the control group a 2-year median survival time, but this time we've put in a hazard risk ratio. And so you're either going to know one or the other. And knowing one, you can usually get the other one anyway. Okay. And so accordingly, oops, there's the mouse. There it is. Accordingly, we change what we're looking for over here to a hazard ratio or relative risk. Okay, so that's a real whistle-stop tour around the PS package. Obviously, you can go in and play and look at all different types of calculations that you may or may want to do in your research. Those are the major designs that are used, or the most common designs which are used in medical research. Okay. The other one, there's a few more caveats around randomized controlled trials, which are considered the gold standard. And the goal of the randomization itself is to produce groups with the same probability of treatment success. So when we talk about balancing baseline characteristics, that's usually what the goal of the randomization is, and also to wipe out major sources of operational or recruitment bias that can come in as a result of not using it. You can get that information back, though. If you don't quite get balance at baseline, you can include any imbalances, those as covariates, in your final analysis to adjust for that. Okay, and when we talk about control, we refer to the comparator group or placebo, although increasingly it's not considered ethical to give placebo as if there are any alternative standards of care or treatments. And the choice of the comparator group will determine the clinically relevant difference, or whether the study is an equivalence trial. I don't cover on this sample size calculations for equivalence trials. I would strongly recommend, if you don't know what you're doing, that you speak to a statistician, because you kind of have to rethink things a little bit backwards to be able to understand equivalence. Common question I get asked is, how do I know what the variability is? And there's a whole range of different ways of finding this out. Usually, if your own previous research work may tell you, or if you've done a pilot study previously, you can look at the published clinical trials which are already available on the same outcome, but be very careful that you look at the target population that was performed on, because most populations are heterogeneous anyway, and the more variation you have in your population, you have to take that into account with the more variation in your trial and the larger the sample size that you're going to need. Sometimes, in the past, when I worked in the pharmaceutical industry, we were at that cusp of going from animal studies into human studies, and sometimes we would use multiples of the variation in lab animals or larger primates. And for studies restricted by resources, you may want to just consider a more homogeneous sample, knowing that you'll have lower variation. So if you find you do your sample size calculation and you can't afford to do that study, you might want to reduce your variation by looking at a more homogeneous, a more similar group of individuals. Yeah? Because the more similar those individuals are, the less variation there's going to be in your outcome. So clinical trial, so sample size calculation is a little bit of a black art. You have to play around with it, and really often we're just trying to match it to the resources which are available to us. However, once you start messing about with your inclusion-exclusion criteria, you also affect your generalizability of the results. If you use target population A, you can only generalize your results to that population A out in the wider external to the trial. Another common question I'm asked is when should I contact the statistician? Please contact them before you start designing the study, because they might be able to suggest alternative ways you can approach it. If you come to a statistician and just says, this is what I'm doing, just give me the sample size calculation, you won't get very good value for money out of the statistician. They will just give you a number back. What they won't tell you is if you design your trial in this way, actually you could do fewer numbers. If you want to look at this group and this group, then we need to up the numbers to account for this. There's a lot more flexibility and give and take around designing a trial, There are other approaches, other outcomes, other ways to standardize and reduce variability that can control this really precious resource that we have to conduct our medical research. Much harder to say where you can find a statistician nowadays. In the tertiary hospitals and the research institutes, often statistical support's offered. Frequently you don't pay for those services, but it's important to inquire when you contact them. There are some contact details on the handout, and I believe those are up to date. If you're a postgraduate student, usually there are consultancy services available via your university to support postgraduate research, but not necessarily if you're on a master's course where they are teaching units as opposed to doing a research project. The other thing to optimise is the amount of time. So if you know you're only being given 15 minutes or 13 minutes worth of free time from a statistical consultancy group, it's good to go along prepared. So in which case, there's a little checklist here. If you're going along and asking someone else to do your sample size calculation, or even if you're compiling it, compile this information for yourself, just make sure you can click off everything on this list before you start. Okay, so thanks for everyone's time today. It's a great opportunity with the social isolation that we're all going through to update all of your skills. There's lots available on Coursera. There's amazing resources around statistical analysis and sample size calculation on the internet. What I can't do is validate which ones are worth watching and which ones aren't for you, unfortunately. But the upcoming research skills which are going to be available on the 30th of October is using REDCap for your data capture and management. And then on the 13th of November is grant application and finding funding. And grantsmanship is a really important skill. Please complete your, complete your evaluation forms and send those in to us. They're very important. And again, thanks for everyone's time today. If you have any questions, it's probably easier to send them to me. Or via the or if you can write them down on your evaluation forms and ask me to call you or contact you. I think that might be easier than actually answering questions in the forum we're in today. But thanks for your time. Have a great weekend, everyone, and keep safe. I'm happy to answer any questions now if anyone in the room. Thank you.
Because I'm pregnant, just friends brings me to I can't sleep anymore.
I was the same. I used to have about 4 cushions.
Yeah, this is how I'm sleeping now, and then every time I need to turn, it's still.
It was dreadful, wasn't it? Yeah, after that hour you think.
So let's say this night, if I can't sleep. What did you do?
The meeting